Welcome back to DemystifySci. I'm Shiloh.
I'm Anastasia.
This is the podcast where we search for the theories that will change the world, and we have one of those for you today.
Back in January, we released a conversation with cosmologist Brian Keating about the cosmic microwave background radiation and the physical theory that underpins it, which is this thing called blackbody radiation. After the conversation, we got a lot of feedback where people listened and they enjoyed it and they saw that something was happening, but we didn't manage to get across why it is that we care so much about this esoteric physical law that 100 years ago was used to rationalize the kind of light produced by heated bodies.
They didn't understand why Brian was so upset about what we were saying.
Yeah, that's a great point. People saw that something was happening, and everybody was very emotional, and it was a very intense conversation about a very esoteric topic. And we've been meaning for a long time to sit down and debrief what happened during that conversation and to try to explain why it is that we think that blackbody radiation is so important. And there's nobody who is more important for this conversation than Pierre Marie Robitaille, who has been the leading scholar of the fundamental physics of blackbody radiation for at least the last 20 years. He runs a YouTube channel where he shares a lot of his work called Sky Scholar. He's written hundreds of papers on the subject, and Pierre is basically saying that there was a mistake made about the way that we interpret the physical cause of blackbody radiation that has expanded and metastasized through all of physics. Yes, Planck solved the equations and he figured out a way to relate the shape of the radiation spectrum produced by a heated body to its temperature, but he did so by completely ignoring the physical nature, the physical lattice, the material properties of the body that is producing that radiation. And what has happened as a consequence is that we have come to live in a world where the cosmos is filled with impossible objects. You have white dwarfs and neutron stars. These are ultra-compact, super dim, super hot objects where a teaspoon of a neutron star weighs as much as the entire Earth. And there's no real physical explanation for how something like that could be possible. And Pierre Marie's work is centered on the idea that it's actually there's no reason for how it's possible because it's not possible. Physics has made a terrible, terrible mistake about what blackbody radiation tells them about the nature of the body that is producing the light. The argument that we give here is that if we actually physicalize the basis of blackbody radiation, if we ask the question of, okay, well, atoms produce light, and then, small assemblies of molecules produce a different kind of light, and then larger assemblies of molecules produce a new kind of light, and then you have this extreme of blackbody radiation where all of a sudden there's this perfect relationship between the light that's produced by the body and the shape of its spectrum. That tells us something truly fundamental about light, and it gives us the ability to look out onto the stars where the only information that we have is light. We live in a universe where if you're looking at something that's millions of light years away, the only information that you have is the kind of light that it produces. And so right now we operate with a theory where, it just does all kinds of crazy things. But if we have a physical theory for it, then we have a way forward where we can actually create physical theories of what the stars are and what they're doing and why they look the way that they do, without shrinking them down into objects that have 2 solar masses in a 15-kilometer radius sphere. These things are a solution to the problem that has come from a lack of physical mechanism for the source of blackbody radiation. And so our conversation with Pierre Marie Robitaille is divided into 2 episodes. In the first episode, we sit down and talk about why it is that we care so much about this strangely esoteric piece of physics that has been on the back burner for 100 years. It's considered a solved problem. And we go through the fact that there needs to be a physical basis that explains the difference in the kind of light produced by individual isolated gaseous atoms and the atoms when they're inside of lattices and the kind of lattices, these molecularly bonded atoms that are capable of approximating the pure mathematics of this Planckian spectrum. They're different things, and there's a physical reason for why the world looks the way that it does. And in the second part of the conversation, we talk about how all of physics is going to change on the basis of this apparently small correction. Because everything from the nature and structure of the stars, down to what it means for something to have a temperature, falls out of this new physical, material understanding for why certain bodies produce a spectrum of light that perfectly reports their temperature.
And searching for a material foundation in physics is something that we have been hot on since the beginning of this project. I would say it is primarily what we do here with respect to physics. It is really the only thing we can contribute because the mathematics are phenomenal, the experimentation is phenomenal, but oftentimes the physical material basis is completely absent. We are super excited that we have completed a very large-scale project. We have written a book about our perspective on how we can retune physics to be closer in line with the material reality that we know well from our daily existence. And so if you would like to pick up a copy of that book, we have it on pre-sale at this moment. It will be out in general sales very, very soon, and you can find a link to that in the description. It is called Paradox Lost: The Material Principles of Natural Philosophy. And in many ways, it overlaps very deeply with the conversation we're having here with Pierre today.
And the reason that it overlaps so deeply, which I think that I buried the lead on this a little bit, is that true physics, where we examine what it is the black bodies are doing to produce their light, is a link that allows us to finally understand quantum physics. Because the same way that it took us forever to figure out what it means for heat to be a fluid, and then we discovered that it actually was the motion of molecules, the exact same thing is true about black bodies and what they tell us about the very nature of light, the very foundation of quantum physics. And from them, we can see that the world is far less weird and spooky than people are trying to tell you that it is.
Thank you to folks who have been buying our record and supporting this music project. I'm super stoked to also announce that we have started recording our second album, and we're really only able to do that because of you who have bought this record in the first place. It is making it possible for us to do another one, and so I'm super stoked. If you want to pick up a copy of that music project, there will be a link in the description, and you can check out a little bit of it at any of your streaming platforms. Our music project is called Secretary of Nature.
And if you want to support the podcast, if you like what we do, come over to patreon.com/DemystifySci. You can support us for 75 cents a week. We have intentionally set that price low so that if you believe in what we do, you can support us no matter what your current economic conditions are, because there are very few things that you can buy for 75 cents a week and very few things of such immense value that you can contribute to at such a low rate. If you don't have 75 cents a week, though, you can just hit subscribe because it helps us grow the channel. It helps us get better guests. And this is the way that we can ensure the renaissance that we really believe is coming for physics and for all of science actually happens. And you can help us do that. Enjoy Dr. Pierre Marie Robitaille. He is a titan of the modern scientific landscape. And before we get there, check out a little sample of our latest music. See you next time. I really think that we should start with a discussion of why is this piece of math that is at the center of the quantum revolution so important? Because it seems like an esoteric detail of nature. Okay, so some stuff makes light based off of its temperature, and some stuff is more accurate in the light that it makes in terms of reporting its temperature. Why does anybody care? That just seems like such a tiny little minute detail of physics that only the most hard-bit nerds would spend their lives thinking about.
It turns out blackbody radiation it's at the center of all of astrophysics. I mean, it's at the center of our understanding of the stars, the temperature of the universe, it's one of the big pillars of the Big Bang. So, we have this principle of physics, and we use it everywhere. And if we're wrong about the principle, then everything's going to collapse. It's like you've built an empire on a house of cards, and you pull one card and they all come tumbling down. And I think that's exactly what's happening here in astronomy. I mean, so I think I can start with in 1859 with what Kirchhoff said, right? He derives a law from mathematics. There's only math in it, and he makes it a law of physics. And laws of physics have to come from experimental evidence, right? You don't make laws from mathematics. You observe nature, and then you try to use mathematics to help us understand nature, to make it clearer to everyone. We can put an equation to this. I guess we'll go back to, the fact that objects emit light. I mean, that's well known. All objects emit light. You and I emit light. All of us emit light. At 11 microns in the infrared, we are very, very good emitters of light. And people who use IR cameras know that. But all objects emit light. And in the 1800s, 1700s, people got fascinated with this, about the ability of objects to emit light. And they discovered, that when the object was, if you put soot on things and you made them black, they became really good emitters. When you heated them, so they just took lamp black, which was soot, and then they'd coat spheres with lamp black, and they'd call that a blackbody. At first, it was just like a sphere. It was an object. Then they heated it, and then they recorded the emission that came off of it. And then they realized that, wow, when things are black, they really emit well. Actually, you see that in nature yourself. Like, if you're walking on your cement driveway and then you go walk on the paved road in the summertime, you'll find that the pavement's a lot hotter than the cement driveway, right? So the pavement is a really good absorber and emitter of light, whereas with the cement, it's reflecting part of the light that's coming in from the sun and hitting it.
I have a good sense of how motion became the way that we think about heat, right? So there's the idea that it's some fluid that permeates all kinds of stuff, and then Rumford does the cannon boring experiments, and they realize that there's actually an inexhaustible amount of this fluid in a substance, and they're like, oh man, it must actually be something about things moving past each other that generates temperature. But I just realized as you're telling this story about this fascination with objects emitting light back in the 1800s, I don't have a very good picture of how they realized that heat was also light.
So what they did was they were able to observe the kind of light coming off an object, and it emitted a certain spectrum. They built these at first they built objects that were black, they were coating with soot, and then they discovered that, well, that was not giving us a well-controlled situation because the room was in there and all that. So then they started building cavities, and they lined the cavities with soot, or they built a graphite cavity with graphite walls. They put a little hole in it. And then they were able to control the heat that they inputted into the walls of the cavity. So they knew, okay, now I can put this in an oil bath, for instance. I know the temperature of the oil, so I know the temperature of the cavity. And then they could look at the light coming out of the little hole. And then they came to the realization that, well, the light that came out of the little hole was always the same. It depended only on the temperature, right? But in those cases, they were using soot inside. If you read Planck's book on heat radiation, he always put a little piece of carbon in his cavities, right? So what was that? That was like a perfect absorber. He was putting a perfect absorber in there, right? And so they were working with perfect absorbers. Actually, Kirchhoff was talking about, a layer of soot infinitely thin. He knew he took very little soot to make the wall black. And that was the beginning of this adventure down. These became called blackbodies, So there were cavities that were empty, and they heated them by placing them in an oil bath, and or you could heat them other ways. Just increase the temperature. You know what the temperature of the wall is, and then they were able to describe the light that was coming out.
When you say they give off the same kind of light, you mean the different colors that come out. So the light comes out, you split it with a prism, and then it has this very distinct intensity per color profile, a fingerprint. That's
Right.
what comes to be termed the black body spectrum, right?
Right. That's called, yeah, that's a blackbody spectrum. And it's characterized a very specific behavior. At low frequency, it moves with the square uh, of the frequency. And then at high frequency, it falls exponentially. And then the peak, which became called the Wien's peak, if you looked at the temperature where the peak was in this distribution, then you knew by Wien's displacement law, just multiply the temperature by a constant, and that was related to the peak, the position of the peak.
The wavelength, the color, right?
Right, the wavelength, and that was related to the temperature. So this was such a nice, here we had this beautiful curve, and then Planck came along and he gave us the equation for the curve. But what's interesting about the whole thing is that we never really, because Kirchhoff came along, when Kirchhoff came along, he said this process is independent of the nature of the walls. He just said that outright in 1859, and no one ever questioned it. He wrote a paper, and this became known as Kirchhoff's law in 1859. But then just a couple of years later, people started criticizing that proof, and that proof collapsed. So then Kirchhoff came up with another proof, again a mathematical proof, and that proof collapsed.
Kirchhoff is saying that it's not just black bodies that give us this nice profile, but any body should be able to do this.
If you had a box, you had a cavity, and had a little hole in it, the nature of the walls didn't matter at all. If you brought them to the same temperature, you'd always get the same curve.
No matter what they're made out of. That's what you mean.
Doesn't matter what they're made out of. It's independent of the nature of the walls.
And the problem is that all of the studies were done with this particular soot-covered or graphite substance, right? So you're extrapolating wildly from this very particular material environment to everything all of a sudden. And it's just an assertion that's never really followed up, chased down, or validated.
Well, there was never an experimental proof. As a matter of fact, there was a guy called Stewart who he was in Scotland, and Stewart wrote a law of emission just before Kirchhoff. And Stewart never claimed independence of the nature of the walls. He just said the ability of an object to emit is equal to its ability to absorb. And that became known as Stewart's law. He just took two plates to make this proof, and it was an experimental proof. And then Stewart and Kirchhoff get into a pretty big heated argument, because Kirchhoff then publishes his law and Stewart objects. And he basically complains that Kirchhoff wrote a law of physics without any experimental proof. So then what happens is, and this is where the nature of the walls came in. So for physicists, you have these two terms, the ability to emit and the ability to absorb. That's called the emissivity and the absorptivity, for instance. Those are related at a specific frequency. So at different frequencies, you can have different emissivities, you could have different absorptivities in a material. Okay, but whatever you're going to have in that material, even if the shape isn't pure, like you're not in the cavity now, the emissivity and the absorptivity will always be equal. That's what Stewart showed. And then Stewart objected to Kirchhoff, saying, hey, it's independent of the nature of the walls. And then Stewart told him, well, you didn't do any experiments. He complained. And he even complained that nobody can follow Kirchhoff's mathematics. Eventually, Kirchhoff's math collapses. He tries to write two proofs. They both collapse. Then Hilbert comes along, and now Hilbert's a great physicist, and in 1913, he comes along and he gives a lecture and he says, there's no valid proof of Kirchhoff's law. Well, now this is a problem, because in 1901, Planck writes his equation, and the left side of Planck's equation is emission over absorption is equal to some function. And that on the left side was Kirchhoff's law, the ratio of these two things, right? And so now what happens now, you've got this equation, it's the correct equation, but Planck, when he writes a book, The Theory of Heat Radiation, he says, well, the first thing I have to do in this book is I have to prove that Kirchhoff's law is right, because it depends, his own law depends on, I want to apply this to everything. It's independent of material substances, okay? And so then he writes a proof of Kirchhoff's law in his textbook, And that proof, unfortunately, it's terrible. And so we went through, Steve Crothers and I went through, and there's a paper that we wrote and published outlining all the problems in Planck's derivation of Kirchhoff's law. And Planck himself in his book, he actually realizes that, well, in a perfect reflector, we're going to have E over A, that's going to be 0 over 0. So that's undefined. And Planck knew that, in a perfect reflector, it's undefined.
Like if you made the cavity out of like polished silver or something.
Yeah, if you made it out of polished silver, right? Well, then the cavity, Planck himself says anything could exist within such a cavity. And then in his book, he says, but as soon as I put a little piece of carbon in there, then that acts as a catalyst and I get the right distribution, okay? And so he attributes to the piece of carbon just catalysis.
I actually have that quote. Can I read it?
Yeah, you can read it.
Okay, so in the theory of heat radiation, he does this entire long proof of how Kirchhoff's law is correct, and then kind of at the end of it, he's making some acknowledgments of the experimental conditions. And he says, the changes in the heat of the carbon particle may be entirely neglected, for the carbon particle exerts only a releasing action. From a thermodynamic point of view, this process is perfectly analogous to the change produced by a minute spark in a quantity of oxyhydrogen gas or by a small drop of liquid in a quantity of supersaturated vapor. In all these cases, the magnitude of the disturbance is exceedingly small and cannot be compared with the magnitude of the energies undergoing the resultant changes, so that the carbon particle, the spark, or the drop need not be considered.
Well, and this was a major, major error on Planck's part, because a catalyst works by lowering the activation energy. Let's say you have a process going from this level to this level, to a lower level. But in order to get to this second level here, you have to go through the activation energy. You have to go up and then down to where you want to be, right? That's what a catalyst does. It lowers the activation energy down here, and then the reaction takes place. But that's not what's happening with the carbon particle. It's a perfect absorber. It's doing work. So a catalyst is lowering activation energy, sometimes by coordinating the molecule that's undergoing the transition, right? It arranges it properly so it can meet with its mate, and then the reaction goes on. So the catalyst is just, you could think about it as a lock and key, right? These things come together, and then all of a sudden, that's how an enzyme works, right? But an enzyme is a catalyst, right? It doesn't change because it's making an enzymatic reaction. But it takes the two reactants and brings them together and then enables them to react without itself changing. That's how a catalyst works. And a catalyst isn't doing work. But for Planck, what he missed was that in a black body, the carbon particle is doing work. When you change one form of energy into another, you're doing work by definition in physics, and Planck missed it. So here's the thing. So Anastasia actually, in her discussion with Brian, she actually stated this very well, and I've stated it before, so I'm hoping she had read my papers. But she stated it very well. So what happens in blackbody radiation? You have light that enters this body, and let's say you have this cavity, and there's a little pinhole, and I'm going to send light into it. And now the light is absorbed by the wall. It's not scattered like Brian says. It's vacuum inside. Okay, so the light enters, and then it's absorbed by the wall. And then Anastasia properly stated it. Now it transformed the light into heat within the wall. The atoms start vibrating in the wall, and then they re-emit light, reflecting their temperature. Okay, so I've said before, a black body is actually a transformer of light. It changes light from one distribution of energy into another. And when you do that, you're doing work. So black bodies do work. And that's why It's not independent of the nature of the walls. The walls are absolutely critical. Now, let's go back to why that is. Shiloh brought up the silver cavity, right? The silver cavity is just a beautiful example. And we use it every day in microwaves. That's how our phones go. We have microwave technology today. We have lasers today. Why is that? Because we have cavities and we put radiation in the cavities, and then we could build standing waves inside those cavities. Now, Planck could have never known that, right? Today we can make reflectors that are much, much even better than polished silver. Amazing reflectors. And so what happens is then you build up standing waves in these lasers, right? And that's how we can get such amplification of light in a laser, because we have two mirrors and we're amplifying the light between them, and eventually it goes out. And so in a blackbody, light is thermalized. It's a thermal process. Work is being done. But in a silver reflector that Shiloh alluded to, there's no work being done. And because no work is being done, you get to build up standing waves. Nothing is happening to the wave. Now, the reason that's important, that's how MRI works, right? We also want cavities in MRI that aren't going to do work on their radiation, right? We're sending a signal into the patient, and we're going to get a signal back. And we'll have a coil around their head. It could be even a cavity. We can put, I actually did an experiment where I had a sealed cavity, and there was just a little port that would bring in the radiation into the sealed cavity. And inside of that, there was a sample, okay? And when I sealed the cavity like that, what I found was that the power required to get the image dropped phenomenally, okay? As a matter of fact, the power was so low, this was done on the AT, the power was so low, instead of using 90 watts to invert the spins, when I sealed the cavity, okay, it was milliwatts. I didn't even have to use the amplifiers. I could do it directly from the low power source that came out of the spectrometer. I didn't have to amplify that source. Okay, so why is that? That's because perfect reflectors don't do work, right? So you get standing waves in them, and then you can get very good. So what happens in MRI, you end up getting what's called a very high Q, a very high quality factor. And so the image, the signal to noise is very high.
A very specific frequency.
At a very specific frequency, you can get standing waves that build up.
This was actually the classical theory for blackbodies, right? So they thought that the cavity was filled with these standing waves, and they calculated how many low frequency ones could exist in the cavity, and obviously the lowest frequency is bounded by the size of the cavity. And then they kind of figured that, well, as temperature goes up, it just kind of gets filled with this infinite number of standing waves.
Well, Planck used oscillators. His oscillators weren't standing waves, really. He used oscillators.
Well, he was operating off of oscillators, but I'm surprised by how the classical model that preceded Planck might have led him to make the mistake, because he was operating with this standing mode theory, where it was actually the cavity.
Right, and that's the Rayleigh-Jeans error, by the way, right? The Rayleigh-Jeans catastrophe with the classical.
Yeah, let's talk about that a second, because I don't think that we've underscored how important this is to the development of modern physics in general yet, right? Because the blackbody is not just important to astrophysics and cosmology, which I want to get to eventually, but it sets the stage for quantum physics as well, right?
Right.
And so what happened with the failure of the classical model? Why was Planck even interested in this?
So I tried to describe this curve, and hopefully you could put up a picture of a blackbody curve. In the low frequency region, right, the curve moves with the square of the frequency, right? So and Rayleigh and Jeans had tried to solve the blackbody problem, and basically it just kept moving up, and that was called the ultraviolet catastrophe. As you move towards the ultraviolet, it just went to infinity. And then Planck's solution corrected that.
Which was obviously not the case, right? We should say, like, obviously you didn't get infinite quantities of light in the ultraviolet region. That just wasn't happening, and they knew that wasn't happening.
It was wrong. So Planck gives the correct solution. Actually, Wien gave a solution that was close, but not quite right. And then Planck gets the correct solution. And when he gives a correct solution, he introduces the quantum of action.
Yes.
So H nu gets introduced and physics becomes quantized. So it's extremely important. Now, when I talk about black body radiation, I'm not taking anything away from Max Planck's equation. Like, his equation is correct. For a black body, it has to be a black body. It just doesn't apply to all materials like he tried to claim. So it has a lot of consequences that part of what he claimed is incorrect. But he did get the equation right, and he therefore quantized physics. But in doing so, he believed it was independent of the nature of the walls. Now, another interesting aside here is that Albert Einstein, he wanted to try to understand, well, what's causing black body radiation? Apparently, he spent 4 years of his life on it, and then he gave up as a hopeless undertaking. So now maybe we could talk a little bit about processes in physics and chemistry, which we whenever light is produced, there's a field of chemistry and physics that's called spectroscopy. And we do it in the laboratory, and the astronomers are also doing spectroscopy. Now, as a fun thing here, I'm an MRI scientist, and I've said this before at meetings, that Ed Purcell, which I was fortunate to meet once in my life, he won the Nobel Prize for MRI. But he was using these spectroscopic methods, and he applied them to the galaxy, and then he applied them to MRI and to NMR, nuclear magnetic resonance, which is the father technique of MRI. And he applied them to both, and he wins the Nobel Prize. He shares the Nobel Prize with Felix Bloch for NMR.
So spectroscopy is the splitting of light into its wavelengths and measuring the intensity of each color. And a lot of people don't think about things like MRI in terms of light, perhaps, or even radio waves. But right, you're talking about huge wavelengths of light, right? So we're talking about light on this giant electromagnetic continuum. And we're talking about ways of analyzing the power of each color or each wavelength, if you want to consider it that way. It's obviously you can't see the colors of radio waves.
So there's light coming at us from, in astrophysics, they're sampling light from either the stars. They think they've monitored the light from the early universe. And these are all spectroscopic things. Like in the sun, we see many spectroscopic lines, and that enables us to identify all the elements on the sun, at least the ones that are above the photosphere. We can see those elements. We can see their signatures, both in the chromosphere and in the corona. We're able to tell what chemical species are there because of the way they either absorb or emit light. Okay, so the Fraunhofer spectrum in solar physics is absorption of light. In the chromosphere, you have emission of light, and in the corona, you have emission of light. So by looking at light...
Did you mean the photosphere, by the way, not the chromosphere, for the emission of light?
The chromosphere is emitting distinct lines.
Lines. Okay, so you're getting more of a continuum from the surface of the sun.
Photosphere is continuous. It's what we consider a black body. So again, this is related because the sun and the stars, they're treated as black bodies. The sun has a curve that's very close to the black body curve. So astronomers, if you make errors in understanding how black body radiation works, you're going to make errors in how you view the sun. So it's extremely important that we correct errors in black body radiation. So as spectroscopists, whether you're a chemist, like I was trained as an inorganic chemist, or whether you're a physicist, or whether you're an astronomer, you're going to be trained in spectroscopy, and you're going to use the exact same method. The same methods, the same principles. The only thing that differs is your sample, right? So I ended up going into medicine, and then I was doing spectroscopy, studying the heart, or then I started doing imaging. So I was doing these things in medicine, right? And before that, I was doing nuclear magnetic resonance spectroscopy on vitamin B6 and its interaction with polyamines. And so that was just biochemistry. Okay. So these are all things as spectroscopists, they can work on all kinds of different things, but your training is very similar, whether you're a physicist or a chemist, it doesn't matter, or an astronomer. There's certain principles of spectroscopy, you're going to follow them. And what's happened to me is that I discovered that some people were not following the principles, and then I went after it. So
Let's talk about the principles in a second. But spectroscopy was invented by a couple of amateurs, from what I understand. And there's actually this amateur couple. I think the husband was a physician, and his wife, and they were making their own telescope lenses on their wedding night. They actually went shopping for skylights, the skylights, because they wanted to melt down the skylights that they would get on discount and make lenses. And they were some of the first people who were putting prisms in front of photographic plates and splitting the component lines. And tragically, the husband died at a very young age, and the wife ended up donating all of their telescopes to Harvard. And they ended up being part of the whole Pickering, I think his name was Pickering, the gentleman there at the time, absorbed all of those telescopes.
I didn't know that story.
It's a really cool story because, at the heart of this is kind of these weirdo outsiders who are really making some incredible advances.
Science is linked. You can come from all kinds of different directions. And usually, like, let's say for me, I did MRI. I should have stayed in it for the rest of my life. But then my interest changed, right? And then I ended up going into astronomy. And I had the tools to do it. But actually, I was extremely well prepared, which most people don't realize that, because I understood the hardware. I understood the theory. I was trained as a spectroscopist. Because I worked in a radiology department, I knew a lot about imaging and imaging principles. So it was just like, wow, I just got to be trained just the special way, all my paths. I remember as an undergraduate, I took modern physics, and, I hated studying about blackbody radiation. When you study blackbody radiation, modern physics, unfortunately, they don't tell you how it works. They just tell you, well, it's independent of the nature of the wall, and you're going to get light out of this, but they don't tell you why are you getting the light. And so that always bothered me. I took the test and passed modern physics and moved on. And then after that, 20 years later or whatever, maybe not 20 years, I can't remember, maybe 9 years later, I was a professor. And then I guess it would have been 20 years when I built the AT and then started thinking about blackbody radiation again.
I think everybody listening has probably had that experience taking modern physics, taking physics in college. You don't have time to really get to the bottom of where these things come from. You just learn the equations, you learn how to, master the problem set, and you move on.
And something bothered me about blackbody radiation. And then when I was working on, so blackbody radiation is also called thermal radiation because it has to do with heat, right? Thermal. It comes from temperature, right? So thermal radiation, blackbody radiation, a lot of times people use these terms interchangeably. It's a thermal process to get blackbody radiation. But what's a thermal process? So when I was doing MRI, we have a property in MRI called the T1 relaxation time. You're exciting a spin, and it's going to go in the transverse plane, and then it's going to relax back. I mean, we don't need to know the details, but when it's relaxing back, Bloch had called that the thermal relaxation constant. Today, we call it the spin lattice relaxation constant. But it was, so you see now we're talking lattice and we're talking thermal. And that's what happens in MRI. You have a thermal process. So I'll tell you a little bit about MRI. If you let's say that I can accelerate you into an MRI scanner at the speed of light and try to take an image, would I get one? Like, you go in and I stop you instantaneously and I pulse and I try to get the signal. Would I get an image? The answer is no. And the reason is because it takes time for the protons in your body to become aligned with the magnetic field. That's to become polarized. And what's doing that is the lattice. The lattice is an important part of doing this, okay, of polarizing the spins. So let's say you describe a process like MRI. You say, okay, well, what's the setting? So I always say there are 5 things in spectroscopy, and this is all spectroscopic processes contain these 5 elements, except blackbody radiation, and I'll show you why it's so important. So for people who know some physics, we have something called the Lyman line, the Lyman alpha line. So if you have a hydrogen atom and it has an electron and a proton, and the electron is in the second electronic shell, and it drops down to the first shell. That'll produce an emission line. It's called the Lyman alpha line. Okay. Now, let's say I want to describe, well, what does it take to get a Lyman alpha line? Well, you need 5 things. The first thing you need is the setting. Well, the setting is the hydrogen atom. The next thing is you need energy levels.
It's in a gas too. It's just an atom all by itself.
It's in a gas.
Right? That's the context.
So you need a hydrogen atom. It's in a gas. Then you need energy levels. You're going to need an electron. It's going to be in the second orbital, and it's going to drop to the first orbital. So the second and the first orbital are the 2 energy levels. Then you have a transition species. That's the electron. Okay, the electron's making the transition. Then you have an equation, which is describing the light, and then you have the light, right? So you have these 5 things. You have the setting, you have the energy levels, you have the transition species, you have the light, and you have the equation that describes it. Now let's look at another example, MRI. MRI is fun because it's one of the more complicated spectroscopic techniques. But what would be the setting? Well, the setting in MRI is, well, you need a big magnet, and you're going to need, you have a magnetic field, you're going to put a proton, you're going to put protons in there, but they have to have a lattice so that they're polarized. So the setting is a magnetic field, protons. Now I'm going to do proton MRI, protons, and then a lattice. They have to be within a lattice so they can be polarized. Now, let's say that we can also do MRI in a gas like helium-3 or xenon-129 to look at your lungs. But, well, helium doesn't have a lattice, right? Or xenon-129 doesn't have a lattice. So how do we do MRI on it? Well, what we do is we go to a laser lab and then we optically pump this to polarize the sample. Then we take the polarized light and it's in a container, and then we have the patient breathe it. So it didn't have a lattice to polarize it, so we did it with a laser. So we optically pumped it, and then we made the polarization, and then the patient breathed it, and then we were able to get the image.
Can we just make sure that everybody understands what a lattice is? Because that's not a word most people use at the grocery store, right?
So if you look, maybe you remember in high school, you had like salt. And they showed you, okay, now salt is a simple cubic. You know, you have a sodium atom, and then you have a chlorine, another sodium, another chlorine, and it makes a little cube. And so that assembly of how those atoms are arranged in salt, they have a specific geometric relation to one another, and that's called a lattice. Okay, so they're bound by bonds. In the case of salt, it's an ionic bond. Okay. In MRI, usually it's covalent bonds. In our body, we have covalent bonds, right? But we have a lattice. Water has a lattice, okay? And water has an extended lattice, for instance, right? People think, well, water, they think, and actually there was a mistake brought by Brian in his discussion where he tried to say that water didn't have a lattice, and then Shiloh corrected him. He said, well, that's my PhD. Water has a lattice. And water does have a very interesting lattice. The most common lattice in ice is ice 1H, which is a hexagonal arrangement in ice. And the closest lattice in liquid water is thought to be very close to ice 1H. So water has an ice 1H structure even as a liquid, but it's a fleeting lattice, as Shiloh mentioned in his talk. It's a fleeting lattice. So the lattice is moving, but it's nonetheless it's there, and that's how we can do MRI on water, right? Because it has a lattice. So we put water in the scanner. Oh, it'll polarize the hydrogens, so the nuclei will align either up or against the field. They'll either be up or they'll be against the field. Okay, and there'll be a Boltzmann distribution of that, and then we're causing the transitions between these two states. Okay, but the lattice is the thing that polarized it, that caused the spins to be, what is the population that's up versus the population that's down, and that depends on temperature. In that equation, in the Boltzmann equation, there's a temperature term, so that depends on temperature. So it's related to this lattice vibrations that we have to give enough time for the lattice to polarize the spins, then we can get the image, right? So if you put the person in right away and pulse, you won't get an image, okay? So now I'm trying to tell you something about MRI. How does MRI work? Well, we have a setting. So remember for the Lyman alpha, we'll go back. We had a hydrogen atom. We had the two energy levels in the atom, and then the electron was a transition species. We had the equation for the Lyman line, and then we had the light. Now in MRI, we're going to have what? We're going to have a hydrogen atom in a lattice placed in a magnetic field. You'll have two states of spins, either up or down. Those are the two energy states. The spin is the one that's doing the transition between the two states. We have an equation called the Lamar equation, and then we have the signal that we detect, right? So every spectroscopic process in physics and chemistry has these five things. But what I thought of, or what struck me when I started thinking about blackbody radiation is, wait, it's the only process in physics where we've never said what are the first three. So what is the setting? What are the energy levels? And what is the transition species? So Planck gave us the equation, and we know we have the light. We have those three. But astronomy has been able to go off the handle. I'm sorry to be a little tough, because they didn't have the first three to restrict them. Okay? So now think of, let's say I'm an astronomer and I'm looking at the Lyman line that comes from a star. I see the Lyman alpha line. So what do I know? As soon as I see that line, I know that, and I think it's at 129 nanometers or whatever. When I see that line, I know that, oh, I have hydrogen and it's undergoing this transition. So because I knew the setting, the energy levels, and the transition species, and I had the equation, and I knew the frequency of the light, I knew, oh, there's hydrogen on that star, right? So the fact that you had all these five things enabled you to study a lot of things about astronomy. But what happened with blackbody radiation is, because we were missing the first three, anything can produce the light. As long as you have thermal equilibrium, that's what they say, is if you have thermal equilibrium, you're going to have this light. And that's nonsense. It's not correct. You have to have a physical mechanism to produce the light.
What is thermal equilibrium? It's a big mouthful.
Thermal equilibrium. So what happens is you want the temperature within the sample to all be at one temperature, right? So let's say we had our cavity. At the beginning of the talk, we talked about the cavity, and we put it in an oil bath, right? We took the cavity, we put it in an oil bath, and that oil bath we heated, and we maybe have stirrers in it, and the temperature is well controlled. Or I had a little paper where I said, okay, let's put the cavity in a helium bath. Let's just drop the whole cavity in a helium bath, liquid helium bath, and it'll be at 4 Kelvin, like liquid helium. And then let time elapse, and the whole cavity will come to 4 Kelvin. So when an object is all at the same temperature, and the temperature no longer changes, okay, there's no forces on it, there's no heat coming in, there's no light hitting it, it's staying at one temperature, then you have thermal equilibrium. Now you could have actually, if light hits it, as long as there's light also going out at the same amount, you could still be in thermal equilibrium, okay? So the balance of heat into the object and heat out of the object has to be equal, and the temperature of the object is all the same. That's thermal equilibrium. Now, obviously, the sun is not in thermal equilibrium. So if you have, like, let's say you have a liquid, if it has convection currents in it, it's not in equilibrium. It's not going to be in thermal equilibrium either, right? If you start heating water on the stove and you're going to see currents in the water, you're not in thermal equilibrium, right? It's trying to reach equilibrium. Some heat's coming off of it and its stuff is moving. So whenever you have convection currents or conduction, you're not in thermal equilibrium, okay? Now, obviously, we have convection currents on the sun. We've known this since the 1800s, or ever since Galileo when he saw the sunspots going around the sun, right? We have convections. It's known. So because we have convection currents, the sun cannot be in thermal equilibrium. But when the astronomers say, well, we are in local thermal equilibrium, we're going to take a piece of the sun so small that it's in equilibrium in that very, very small part, okay? So that's how the theoreticians get around it.
Pardon the interruption, but I have to ask you for a favor. Everybody knows that there's always a paradigm shift somewhere around the corner, somewhere down the road, but nobody really knows how to find it. Nobody knows where it's hanging out in some dingy laboratory basement somewhere. And we have decided that we are going to find those theorists, and we're going to put them in front of you so that you know the direction that the world is going to shift into. And we have decided to do that without sponsorships. We have decided to do that without advertisements because we believe that the work that we are doing is not a billboard upon which advertisements should be plastered as the conditions of our success. And in order for us to be able to maintain that line, in order for us to be able to show that it is possible to devote ourselves to inquiry, to devote ourselves to bringing you the best ideas that we can find, we need your help. We need you to come over to patreon.com/DemystifySci and sign up to support the podcast. You can support us for as little as 75 cents a week, but if 100 of you do that, if 200 of you do that, if 500 of you do that, then all of a sudden we get to be in a position where we can grow this podcast into something that is more than just us sitting in our living room talking to people over Zoom. We can host live events, we can host regular conferences, we can fund the people that have the chops to be able to test the ideas that are being presented here, and we can really grow this into an institution that is going to be the lighthouse for all of knowledge in the world. But we can't do that without you. And so, if you can, come over to patreon.com/DemystifySci and sign up to support the project today. If you can't do that, just hit subscribe. All right, back to the conversation.
I don't think that it's an understatement to say that black bodies are the missing link between classical physics and quantum physics, and the modern physics in general owes a lot of its understanding to this very special experimental condition. And that's why we're so obsessed with it. It really gets a minor shout out in most physics classes, but I want to be absolutely sure that this podcast is able to lay on the table for everybody listening why black bodies are so important to all of physics. It's not this tiny little thing that only even matters to astrophysics. It is part of everything, right?
Before we get into the fact that we haven't defined these 5 characteristics for black bodies, I think that there's something that we've left behind on the table, which is the transition from the kind of light that isolated atoms produce versus the kind of light that those atoms produce as soon as they're in even a molecule that has a couple of atoms in it, versus the kind of light that they produce once they're inside of any generic lattice, versus the kind of light that they produce when they're inside of a black body. Because I think that kind of
Okay, that's a
stepwise
very
change.
good point. So if you have an individual atom, like let's say a hydrogen atom, you're going to be able to have transitions. Now we're not going to talk about MRI or processes like this. Okay, we're just going to talk about spectroscopy, not involving the nucleus. Okay, we're just going to think about the electron. Okay, because there's other things we could do with the nucleus, but we're going to try to talk just about the electron. And there's when the electron's making a transition from one energy level, one orbital to another orbital, it releases light. So the Lyman series is, the light going from level 2 to level 1, level 3 to level 1, level 4 to level 1, and so on. That's called Lyman. Balmer is level 3 to level 2, level 4 to level 2. So the Balmer series ends at level 2, okay? But each one of these little individual transitions gives you a sharp line. So that's what you're trying to get at.
A single color.
Is that in a free atom, you get sharp line transitions. As electrons move from one energy level to another, the lines are sharp. Now, the lines can become broadened if they can become pressure broadened. So if you take your hydrogen and you put it in a container and you put enough hydrogen in it that you pressurize it, the lines will become broad, but they won't become black.
One peak color and spread out a little bit.
Instead of having one single color, now they'll extend a little range of colors around that sharp peak. There'll be a range of colors, right? That's called pressure broadening. If you put a lot of pressure on the atom, on an assembly of atoms, they'll start hitting the wall, and that will cause some interaction with the wall, and then that causes the light to broaden. The atoms gain an attribute, a little bit of the lattice. You're pressure broadening them. Okay.
And that's probably from like collisional interactions inside the system where you can kind of think about it where if the atom produces a single wavelength of light because it's like a bell that rings or like a tuning fork that rings,
Right.
then if you have a bunch of them around, they're just pushing on the atom that's producing the light and inducing these weird harmonics in that fundamental tone. But the fundamental tone remains. Like instead of being this like very, very sharp line, it kind of gets more of this like spread out bell curve shape.
Right. And then the other thing that can happen, you can have exchange. If you have two species and they're each sharp, and you see this in MRI, in NMR, you can have two species that are sharp, okay? But if they start exchanging, they do chemical exchange, then the lines can get broadened and shifted. So you see that in NMR. And that's why when you see a shift of a line in astronomy, it doesn't always mean, if it shifts red or blue, that doesn't necessarily mean that it's due to gravity, like the astronomers think. It could be due to chemistry, and they don't consider that. So now
and then there's a fascinating thing because so everybody probably has in their minds a picture of what this kind of spectrum looks like, because they probably took high school chemistry and they probably had a Bunsen burner and they had that little like thing that they looked through and they saw the little lines. But what's interesting is that for those experiments, we choose very particular substances that will respond well inside of a Bunsen burner. Like but you can always see that if you just put the metal loop into the Bunsen burner without anything on it, and you look through the spectroscope, you then see this background rainbow continuous glow across the entire thing. And if you then go from looking just at the behavior of atoms to then looking at the behavior of molecules that have a couple of atoms in them, the complexity of the spectrum explodes. It becomes much more complicated. Immediately you start to have overtones, you start seeing new light inside of this.
Right. So if you have two atoms like hydrogen chloride, okay, well then you'll have a K and R branch, and you'll have vibrational rotational lines, and you'll see these lines as the molecule vibrates and rotates, okay? And then if you have a very complex atom, a very complex molecule, now you're going to get more and more and more lines. Now, the more complex it gets, eventually you're going to reach the point of a lattice, and this thing becomes continuous, right? Once you start forming a lattice, you're going to start having some continuous emission. So you'll end up like, for instance, aluminum oxide will give you, a very strong band, and the emissivity almost goes to 1, and then it falls back down, but it's really quite broad, but it's just not blackbody. It doesn't look like that perfect blackbody curve.
Lattices do give continuous spectra, but that doesn't mean that they necessarily will report the proper temperature. And this is something I kind of bungled in the Brian Keating interview myself, because I'm sorry about that. I didn't understand this as well as I should have, but the blackbody is particular because the temperature that it reports is reliable, right? But when you have different other lattices, you could perhaps not be getting the right temperature. It's still a continuous spectrum, which is very different than the gas or something like that. But
the spectrum will be shifted. It can be distorted. It's going to be different.
Right. So it doesn't even have to have that same shape as the blackbody curve, right?
Right. And then you were trying to talk about gray bodies, and a gray body is like a black body. It gives the right temperature, but instead of the curve having the right intensity all the way across, it's just the whole intensity comes down on the whole spectrum. That's a gray body.
So I messed that up. So I want to be really clear.
You messed that up a little bit. That's okay.
So what I was thinking, I just want to be clear about this. So the gray body tells you the wrong intensity. The non-black body lattice is going to give you the wrong temperature, if it gives you a temperature at all, because you're trying to fit a black body. It
always gives you a temperature.
Well, you're trying to fit a black body curve onto something that might not be shaped like a black body, right? It might have, like Pierre said, little shoulders here and there, and just be kind of strange. So just let's set that clear.
I think that,
so you can look in the library and you can see emissivity tables, and you'll see all the materials and how they emit. And even within graphite, different types of graphite, they're not all giving you the perfect ideal blackbody curve, right?
Yeah, didn't you tell us that there was like one mine in the world that
Yeah,
produced the
well,
perfect
there's
graphite?
one place where the emissivity from this mine, it was just like perfect, over a small range, right? And in another mine, it's not as good. So even when we talk about graphite, because in mines there's impurities and so on. Even when you look at graphite, well, where was it mined? So these things matter. And that, I think Shiloh was trying to allude to that in the talk when he was saying, well, if we can make the hexagonal planar lattice as good as or perfect or close to perfect, we're going to get great emissivity.
Okay, so this is actually a great segue, because I think that we're ready to really talk about the specifics that make something an excellent blackbody, because as we talk about this, and I haven't really thought about this before in terms of this transition from, heat is fluid to heat is motion. I think that in the subject of blackbodies, there's already so much information that tells us that light is something more physical than the models that we have given it to this point. Because if light was just some strange thing that could come from anything and all kinds of light could come from all kinds of systems, then yes, we would have some sort of weird fluid that just permeates the universe that, the speck of carbon catalyzes into the blackbody spectrum. But based off of everything that we know about atomic light versus molecular light versus lattice light, we seem to have this very clear transition from one kind of emission to a very different kind of emission. It goes from these pure lines of color or wavelength into this really particular curve that reports accurately the
Right.
motion of the atoms inside the lattice.
So the transition species, remember in the setting, I was talking about that, the hydrogen atom. The transition species was the electron, right? But in hydrogen chloride, well, it's vibrational rotational lines, right? So there, it's the rotation of the molecule itself. It's the molecule rotating or it's the molecule vibrating, right? We're not talking about an electron transition anymore, right? These are vibrational rotational lines. And then when we're talking about black body emission, now what do we have? Why does graphite give you a black body spectrum? And the only thing that has left in graphite is a lattice. The graphite isn't rotating, it's vibrating. The atoms inside the lattice are vibrating, but there's no rotation. These atoms are stuck in a plane, right? So in the lattice, in that beautiful, perfect lattice that we care about so much, the atoms are stuck in a plane, in a hexagonal planar arrangement. And actually, Brian understood this. The one thing that he understood, that he said, well, you can't get the CMB from dust. He knew that. And the reason is, which he didn't say, but the reason is because the dust particles are too small to give you the long frequencies, the long wavelengths that he wants, the low frequencies, okay? And that's why you can't attribute the CMB to dust, okay? So we know that, okay? So to get these very long wavelengths that we see in the microwave background, right? We need an extended lattice, okay?
That's very strange that he would recognize, by the way, not to pick on Brian too much, but that he would recognize that the dust can't do it because it's too small, but gases.
No, he didn't know why it did. He never said why it couldn't do it. I know why it can't do it because I studied it. But he just knew that it couldn't do it. But he never stated in the talk why you can't do it. That doesn't mean he didn't know, by the way. Okay?
Do you think that we've made it clear for everybody that there has been an overgeneralization of this behavior to, like, the lattices from the gases, from the imperfect lattices? Those have all been confused in modern physics. Is that abundantly clear for everybody, do you think?
I think that there's like one piece that we need to really like weave into this, which is that it appears that there's something about black bodies that allows us to get at what looks like a molecular theory of light. And
well, there is no theory of why does a black body emit the light. That's the problem.
That's what I'm trying to say, is that the reason that this is so exciting to all of us is that the theory that has been inherent in all of physics, that is cemented in all of physics, is that there's no physical cause for the appearance of the blackbody spectrum. It is just this.
Right, and that's incorrect.
And
it's incorrect. So Kirchhoff made a mistake, and the cosmologists and the astronomers, they just never went back and reviewed. I spent years going back and reviewing the papers and saying, okay, does this stand up? Did this stand up over time? And then what I found is that things collapsed, but yet people still adopted, that what Kirchhoff had said was true, that Kirchhoff's law is valid. I mean, go online, you type Kirchhoff's law of thermal emission, and Wikipedia will tell you all about how true it is. It's completely false. There's no scientific proof of Kirchhoff's law of thermal emission, but the stakes are so high in physics and astronomy that nobody has the courage to dispute it. Things must remain independent of the nature of the walls, because let's say that you say that things must depend on the nature of the walls. Well, that is a very, very bad no-no for astronomy. If all of a sudden a lattice is required, as I've said, you need a lattice, you need a vibrational lattice. What I've said is you need to have the vibration of atomic nuclei within a lattice. Okay? That's why you get a blackbody spectrum. You have these positive charges, and they're moving in that lattice, and that's producing the light. Okay? And physics has never said that. They never gave us a mechanism. They just gave us, we have light, and we have an equation. Okay, and I'm saying, no. It takes more than thermal equilibrium. There has to be a physical mechanism to produce the light in the first place. You need a lattice. So I've insisted you need to have a vibrational lattice. And so once I do that, if I say you must have a vibrational lattice, now I impose it everywhere there's a blackbody. So if there is a blackbody coming from a star, it must have a vibrational lattice. And that's why I said the solar spectrum comes from a one-component plasma that's hexagonal planar. It has this hexagonal planar lattice. And I picked this particular one not by accident. There's something very important about that lattice. First of all, it's the best one to produce the curve that we want
in the laboratory.
Secondly, it permits the intercalate zones that I talk about if you go look at my videos, and then that allows us to explain lots of star types and so on, which you won't get with other lattices.
But there's something kind of schizophrenic here, though, because on one hand, physicists recognize that gases do give individual lines, right? Every single chemist and physicist that I know recognizes this. But at the same time, they say, and this happened at the very end of the Brian Keating interview, he said, well, but since stars can do it, we know that gases can also make black body spectra.
No, but stars aren't gases. That's the whole point. I mean, Brian makes
contested assertion.
Brian makes several statements, and I think these will all, you guys will scroll these, but he says, he asks a question. Let's go back. I think we should cover some of these things because they discuss. You guys are trying to talk about black bodies with him, and he's of the belief that a gas can produce a black body, okay? And it starts with, speaking of black bodies, he said, but this has nothing to do with lattices. You can have a plasma that approximates a black body. And then Anastasia responds, the reason we think that is because we point to the sun. And then he says, no, it's not just because of the sun. In a tokamak, you can produce a black body. Well, first of all, the sun, I'm saying, has a lattice. That's the whole point. It has a real surface, whereas a gaseous sun doesn't have a real surface. So he pointed to the sun, and then he says, but it's not just the sun. So he didn't say, no, the sun is not a gas. He accepts that it is, and gases can therefore produce a black body. And then he says, but we see it also in a tokamak, which is not true. In a tokamak, the gaseous plasma in a tokamak gives you emission lines. You can have some continuous component, but you're going to have emission lines as well.
And emission lines in this case are that you have this kind of continuous spiky hump that's of some shape. And then on top of that, you have these very sharp peaks, which are attributed to, I think it's Bremsstrahlung radiation. It's the changes in acceleration of the components of the plasma that are producing the light as they...
And you can also have transitions within the atom of electrons within the atom in the plasma, it doesn't have to be just the capture of an electron recombining with a proton or with an ion. So he said, and you immediately answer when he said it's not just the sun, it's a tokamak, and he says, Anastasia said they don't produce a black body, and you were right. Tokamaks do not.
And I think that a lot of this is really confused because when people measure the spectrum of the plasma through a little window inside of their reaction chamber, they cannot remove the contribution of the walls.
That's right. And the walls are made of graphite and a tokamak. So, and Brian he dismissed, he said, well, the wall's not important, but there's a graphite wall there. And so you can have a black body appearance because the plasma is interacting with the wall. But he also said, we observe black bodies in gas clouds in the Milky Way. But the problem is gas clouds in the Milky Way are not just gases. There's condensed matter in gas clouds. That's why they have dust problems and so on. Okay. And then he again on lattices. We're just going to talk about things of lattices where it shows the serious. And by the way, this is not a problem of Brian. He is not at fault here. He is just restating what he has been taught. I'm not picking on Brian Keating, and trying to say, well, he doesn't know or whatever. No, Brian is properly describing what cosmology believes, okay? And I'm saying it's wrong, unfortunately. Now, one of the things they say is, if you have a gas and you make it dense enough, okay, you make it dense enough, it becomes optically thick. They call it optically thick. When you make it dense enough, or you make the cylinder of gas that you're looking through so long, you're looking through miles and miles of gas, so it's optically thick. When you do that, then you get a black body. So it's a circular argument. If you have a gas that's optically thick, it's black. The problem is gases are never optically thick, so therefore they're never black. But if you are trained as a cosmologist, you'll be trained. Gases can become optically thick, therefore they can be black. And it's completely false. The stars are not gases. They have a lattice, and that's why they're optically black. Okay? But because he believes that the sun is a gas, he thinks it's optically thick, therefore it's black. But if you look in the laboratory, it doesn't matter how thick you make the gas, it's never going to become optically black. Gases emit in lines and bands. That's it. And they can be pressure broadened, but they will never assume a black body spectrum in the laboratory. So it's completely false.
Yeah, can we pause for just a second? This is really important. I just want to make it clear that, first of all, almost everybody thought about stars as some sort of condensed matter prior to the 20th century. It seems like to me, looking over the history. And you've written a beautiful, beautiful piece, by the way, that everybody should go check out about the history of the gaseous sun. I don't mean to recount it here, but the idea that the sun is a ball of gas is actually pretty modern as an idea. It's relatively modern. That's a new-ish way. That's a 20th century way of thinking about the stars. And perhaps it's worth pausing, because if everything we're saying here is true, and we're also making it seem like it's all pretty obviously true, why in the world would people be committed, these professional physicists, why would they be committed to treating the stars as an exception to the rule? Maybe we can just really quickly outline the history of why that transition happened in the 20th century.
The gaseous sun, it actually was proposed in 1864. And
close enough.
The first person who proposed that the sun was a gas was probably Secchi. Before that, the sun was thought of as a liquid. And before that, a solid. I mean, Herschel thought the sun was a solid with little Solarians on top of it. It was inhabited, right? And they walked on the surface of the sun. And then poor Herschel then discovers infrared light. And he says, oh my gosh, I'm going to cook my Solarians, it's too hot. So then he puts the infrared layer in a cloud above his Solarians, and he puts a perfect reflector. He puts a reflector under that to protect his Solarians so they don't get fried by his infrared light. I love that example of science because it really shows you how creative scientists can be.
Wait, so did the Solarians live mostly in the dark then?
No, well, he must have had a light layer below it. Because for him, infrared, when he discovered infrared light, he didn't think about it as that's the light of the sun, right? He just thought, he just realized it was putting out heat, and he was the one that he discovered infrared radiation.
It really tells you that it was a very different culture of science back then, right? Because he just rattles that off, and he's actually talking about something completely differently in that paper, and he just kind of mentions it, and good luck, like just mentioning something like solarians in the middle of a Nature paper today. I mean,
so when the sun became a gas in 1864, it was really Secchi that said it. Actually, the idea was initially published in a journal called The Reader by Herbert Spencer in England, and Spencer did not sign it. But we're in 1860 here, right? Whatever, 62 or whatever, when he wrote the article in The Reader. And Herbert Spencer was a devout evolutionist. Okay, and so he had some enemies. I mean, he wrote some pretty nasty things about French Canadians, I can tell you, which I had read at some point about not being very intelligent and so on. I take some slight offense, but so Spencer was a caustic person, but he never signed his analysis that the sun should be a gas. Okay, but for him it was like a gas bubble. And then what happened was Secchi and Faye. Secchi was a priest at the Vatican Observatory in Rome, and Faye was a big shot in France. I think he was a minister or something, and he was a well-known, won the Legion of Honor or whatever. And it was Faye and Secchi who made the sun a gas. And later on, Lane comes along in 1879, and he uses the ideal gas law, and then we go into the mathematics of a gaseous sun, okay? Because it was so nice, like with a gas, the math is so beautiful, I remember a couple of stories. First, when L.V. Faye made the sun a gas, he just said, well, if you look at it, he was looking at it with the telescope and said, yeah, the sun's a gas. I mean, it's in 1864. I mean, he can't tell if it's a gas or not, okay?
Well, this was the era of gas lamps, though, and stuff, right? This was when people first started lighting. Artificial lighting was being done with gas lamps, actually. I think that's not a coincidence.
Yeah.
They were also, there was all these thermodynamicists playing with these ideal gas laws, right? Because they're building heat engines for the first time. So everything's a gas to the high tech.
Right, everything's a gas, and the math is so great. And then Lane comes along, and Lane was an American, and he writes the first paper that mathematically treats the sun as a gas. And what's funny about that is, I remember when I first started, for those of you who remember that I took the New York Times ad in 2002. When I first did that, my wife said, well, Pierre, you really have to go and sit in some astronomy courses. And so since I was a professor, I went and sat in the graduate course in astronomy. And the way they start is, with the gaseous equations of state. They don't start by saying, these are the reasons, this is the experimental proof that the sun is a gas. Okay, you give me your proof that the body of the sun is a gas. Okay, but it doesn't start that way. It's all mathematics. We start with the gaseous equations of state, the ideal gas law, and from there the sun is a gas, and we move to this day. Okay,
but this is a really old tradition, because if you look at the way that Newton writes the Principia, he uses mass in all of his equations, but he basically says we're not going to deal with how to derive the cause of mass. It just is. It's a quantity we're going to deal with, and that's the most that we can do. And that's just so inscribed in the tradition of science, that you can start with this assumption about a thing that you don't prove because it lets you go do something else. And it seems like this is the same category of error.
Yeah. Now, in their defense, there is one thing, though, and that is that the critical point of hydrogen, like they knew that the sun is very hot and it's well above the critical point of hydrogen. And for them, there is no way that it can be anything but a gas. So that's in their defense. The problem is that if they had paid attention, in 1935, Wigner and Huntington write the classic paper on metallic hydrogen. If you take hydrogen and you bring it to high enough temperatures and pressures, it becomes a metal. And both pressures and temperatures facilitate this. So this critical point of the gas, it's irrelevant. We've moved to a different material. Okay, and so so I'll give them some defense, but it's a long way since 1935. We've had time to think about metallic hydrogen, and then the eye came along and said the sun is metallic hydrogen. This is the lattice, and I'm quite firm on it. So, but for Brian, we were talking about him, you know, lattices. This has nothing to do with cosmology. Okay, lattices have nothing to do with cosmology. And then, and there's other things. People can read these things, and you can make a black body out of anything.
Yes.
That is false. You cannot make a black body out of anything. And Brian actually, in his talk, tries to argue that you can. It's not a long argument, but he mentions you can make. Given that you can make a black body from diamonds, you can't make a black body from diamonds because they're transparent, and black bodies have to be opaque.
What's crazy is that what we've been talking about, actually, I can see what he means by that, because if you take the diamond and you coat it in something black, you can in fact make it into a black body. But it's the same categorical error made by Planck, where the black coating is viewed as not being important. I think that that's the root of that premise, where he's like, well,
I don't know where he's getting it. He asked the question, can you have a black body that is a gas? And Anastasia answers no, and Shiloh correctly says never. And this is beautiful what Shiloh writes. He goes, there is a material basis for why this is the case. I think physics all has a material basis to it. There is a reason why black bodies give that spectrum and gases don't. Gases have a different limited set of vibrational freedom compared to lattice-bound atoms. And so I think that Shiloh just nailed that exactly correct. And then Anastasia then wrote, only lattices can be be a perfect black body. The quality of a black body depends intensely on its lattice structure. And that is absolutely right. And then Brian says, if you took carbon and atomized it into a gas, could it be a black body? Right? And then Anastasia answers, no. And then Brian says, you are making a statement that is provably false. Well, no, Brian. She's correct, and her statement was never provably false. So Brian has never studied black body radiation. He doesn't understand crystals. I'm a little tough on him here, but he studied cosmology.
But it's not just Brian, by the way. Like, one more time,
right,
like he's just he's a representative of an entire discipline, and he's nailing it for his discipline. Like, he knows his discipline perfectly, in and out. I've talked to hundreds of cosmologists and astrophysicists over this short term we've been doing this podcast. They all think like this. This is not unique to Brian. So Brian is defending the standard dogma.
We can replace Brian with the cosmologist, like the capital cosmologist.
I don't want to pick on him. I'm just saying that, unfortunately, these are the things that are being said and who said them,
Well, I think that the cosmologist represents this archetype of interlocked beliefs that lead to the field looking the way that it does.
Mm-hmm.
And so the interview with Brian represents the perspective of cosmology perfectly. And what we're trying to deal with is the fact that it seems to be an incorrect belief, which seems crazy. Like, it literally seems crazy that we're sitting here.
They don't want to know the truth.
Well, but that also seems crazy.
This is my problem. Let's say that I'm an NMR spectroscopist, and I do MRI, but I really don't care about the setting. I don't care about the transition species. I don't really care about MRI theory. I just want to sample and get the answer back, right? Well, MRI would never develop if that was the case, right? MRI developed because people understood the first three: the setting, the transition species, the energy levels. We understood those, and that enabled us to manipulate how we're going to get the light out or the photons out, right? And what we can do with our equations and play and get our MRI images, right? We had to well understand the first three. But what cosmology has done is we don't care about the first three. Why? They don't care about the first three because they want to play with equations and light. But if we're telling them you need a lattice, the game is over.
Well, I'm going to push back a little bit on that and be a little bit more forgiving, because I think that what they've done is because they have the gaseous stars, it's always their way out, because they're like, look, yeah, in laboratories, for the most part, you need a lattice. I mean, they don't say it that way, but if you pushed them, they would be like, yeah, I guess so. Like, that's how we do it in laboratories. But the stars, we know the stars have almost perfect blackbody spectra, and the stars are gas. That's a foregone conclusion from the 19th century onward. And so for them, there's always a way that nature can use gases to mimic what we see in the laboratory with black bodies, right? So they believe in their hearts that gases can do it. I think that the
Right.
context is just so variable for them, and it's so exotic in the form of these giant, massive balls of gas, that the unusual can be expected sometimes in nature, and that permits them to extrapolate blackbody theory to everything where it doesn't belong.
And the
Right.
fact that it's us sitting here that are saying that something has gone wrong. And I think that the next part of this conversation should be where we dive into all of the ways in which it has gone wrong, because the revolution in the theories of astrophysics and cosmology that this different view requires is immense. It is literally undermining 100 years of published research of the smartest people on the planet focusing on these questions and applying their mathematics and discovering things that are unbelievable in the cosmos. The story that everybody has been getting up on stage at conferences and telling and giving each other awards for. It's the three of us that are sitting here and saying, hey, something has gone terribly
Well, I
wrong.
think it's more than the three of us now. I think people are understanding that there's a problem that's significant. And you know, I look back and I've listened to the interview many times. I would say I pretty much know it by heart. And there are things
Pierre
there are
keeps
things
calling
that
us
Brian
depressed every day. I'm still
yeah, there are
listening
things
to
that
the
Brian
interview.
says that they're just patently false. And the thing that I'm concerned about is that he doesn't care about getting the answer. That it's not important to us to understand black body radiation.
I view it through the lens of this. If I was an avowed atheist and I was absolutely convinced of my belief system, and somebody showed up and was like, hey, I can prove to you that everything that you and everybody that you respect believes in is wrong, and they just showed up in my office and just sat down and started telling me this on camera, I mean, I can hope that I would react better to it than he reacted to the idea that lattices are at the heart of black bodies. But I can also have a great deal of sympathy for him because it's just
Of
these
course.
two random people with a podcast that think that they've solved the last
Well,
century of
that was something
physics.
interesting in the talk when he said, well, I get tons of theories, and we're not trying to do grand unification theory here. We're not trying to do a new theory of gravity, right? We are talking about a problem that has existed since 1860. So when Kirchhoff in 1859 wrote his paper, and that physics, because of the importance of Planck's work, never corrected him, never corrected Kirchhoff, and never corrected Planck. Again, Planck's equation is correct, but there is a setting. And when you make a black body, there's a certain way. If you go to NIST, they don't just make black bodies out of anything. There's a particular way that you make a black body, right? You use graphite still to this day. You still use soot to this day, to make black bodies. Now, you could use other materials. I don't deny that. But there's something interesting about them not understanding properly black body radiation. I'll give you an example. They want to launch a satellite right now called Pixie. The cosmologists do. Okay, Pixie, and that satellite's going to the second Lagrangian point again. And they have a calibrator on that satellite. Now, this is a project. The satellite doesn't exist yet, but they have a calibrator. And this calibrator is a disc with little cones coming out of it. There's aluminum behind the cone, and then there's a black material on top of the cone. And this disc is all going to be kept at a given temperature. It's going to be cooled to a certain temperature, let's say 2.7 Kelvin, and it's going to be a calibrator for their satellite. So there are two errors, fundamental errors in the design of their calibrator. And to understand that, we go to the butterfly. So the butterfly is very interesting because if you look at the monarch butterfly, it has these beautiful, extremely black lines in its wings. They're very black. Now, why are they black? Well, it's not because of a hexagonal planar lattice. It's because they've made these microscopic wedges. And when the light comes in and hits the wedge, it just bounces around into the wedge until it's finally absorbed. And the little butterfly heats himself up by allowing the sunlight to hit that black area, and then it channels that heat away. Okay. Now, if you look at the butterfly in the infrared, so this is a very good absorber, right? But you did it geometrically, exactly like Arcade is doing it on the Pixie satellite, like they did on the Arcade balloon and on the Pixie satellite, right? You're doing it geometrically. You are capturing the light using cones in a geometric manner. And when you do that, what happens? The emissivity is terrible. So what in the butterfly, if you look at it in the visible, you see the nice black monarch butterfly that everybody knows the wings. Maybe you guys can put up a picture of a monarch butterfly. But when you look at the butterfly in the IR, all you see are the veins in the wings. You don't see the black anymore. Why is that? It's because this mechanism of channeling light through absorption, repeated absorption to capture the light and the heat, prevents the light from coming out of this channel, right? So the absorbance from that region is not the same as the emission. And that's what's happening with the calibrator on the Pixie satellite. It has consequences. So there are two errors with the calibrator. So the way that they say, well, this calibrator has a great emissivity, it's fantastic. And I say, no, it isn't. What you've done is you've done a type 7 error. I wrote a paper about errors in calibrations with reflectivity. So the way you do it is you're sending light, you're sending microwave radiation into this calibrator, and it's all absorbed. So because it's all absorbed, they think, wow, the emission is great because there's an equation that says, well, you know, the 1 minus the reflectivity is equal to the emission, right? Well, if the reflectivity is 0, then the emission is 1. So this is, wow, this is a great emitter. But actually, it's a terrible emitter because you've done it geometrically just like the butterfly did. You didn't do it because of underlying structure that was able to absorb the microwave. You did it geometrically. And what's worse is then you cooled down this area. You brought it to a certain temperature by bringing it to 2.7 Kelvin, and you pulled the heat out of it. So the heat doesn't have to leave through emission. It can channel through conduction. So it's not a good calibrator. So by them not wanting to understand how blackbody radiation works, they never learned about the butterfly, and they're making now serious errors. In the Planck satellite, there's a similar error. In their microwave, in the low frequency instrument, they have calibrators. And these are made, they're little aluminum squares, and they have this epoxy material that's supposed to absorb microwaves. But if you look at the spectrum that they obtained from the network analyzer, you see they're standing waves inside their calibrators. They're standing waves. Well, black bodies can never sustain standing waves. You cannot have them. So that means that they're not black. So even the Planck satellite has errors. And I wrote a paper about that. And so this is what happens when you don't care about why do you get a black body spectrum? How do you get one? If you don't care, then you're going to make building errors as well. And then that translates into your scientific errors. So we're going to launch the Pixie satellite, and they're going to say, oh yeah, well, yeah, we did measure the monopole at L2. No, you didn't, because you had a bad calibrator, and I'm saying it in advance of Pixie ever being launched.
It's not a true black body absorption, it's a geometric absorption, which is different from...
Right, it's using geometry to capture the light by repeatedly having the light interact with the material, right? So the light's coming in, let's say you have a wedge, like the butterfly, the light is coming in and it repeatedly hits the sides of the wedge until it's finally absorbed. That doesn't mean that the material itself that was absorbing the light has that high of an absorptivity. Because the light has repeated chances to be absorbed.
And so tie this back to me to why this invalidates the calibrator from working? Because is the calibrator, you're saying that the calibrator cannot emit at this 2.7 Kelvin?
Yeah, it's not emitting as well as it's absorbing.
I see.
Because it's using, and if you look at the paper, I wrote a paper on this about calibration of microwave blackbodies. And what happens is that when the light comes in, on the way in, the light comes in and it gets repeated chances to be absorbed, right? Now, let's say there's a photon that wants to leave the bottom of the channel and it tries to get out. Well, it's going to be absorbed on the way out. So it can't work its way out. So the emission is not equal to the absorbance.
And they're not going to test this before they send this thing to space?
Well, the way they tested it was with reflectivity, right? They sent a wave into it and it was absorbed.
But they're not testing to see if they get the right kind of light back out of it?
No, they check it by reflectivity.
They just believe the absorption and the emission are these perfectly
So they believe that
processes.
the emission and the absorption are equal, but they're not.
But that boggles the mind. Like, you're going to spend $1 billion on a satellite?
The reason they're not going to be equal in the satellite is because they're cooling. So remember when I was first talking about black bodies, you're putting heat into the black body. You're not pulling heat out of it. You're pushing heat into the black body, right? You put it in a heat bath, you're heating the heat bath, and then the light is being produced. And so the way that the heat is escaping, right, is through light. But now if you try to pull heat out of the walls, you don't have to emit light because you're getting the heat out through conduction, which is actually more efficient. So the problem is with their calibrator is they're cooling the back of it. That's the same problem with the Planck calibrators. The blackbody calibrators on the Planck satellite are also cooled. They go through washers through a 4 Kelvin heat shield. So that the heat is being pulled out of the calibrator and can go through the washers to the shield. So they're keeping the calibrator cold. Well, then the calibrator doesn't need to put out any photons. You're pulling the heat out of it. So when you want a black body, you can't be pulling heat out of it using conduction.
And so is the theory of the calibrator that they should be able to point their horn or something towards it and be able to say that, like, this is emitting this 2.7 Kelvin radiation?
They want the calibrator to emit at 2.7 Kelvin, but they have two errors. One, they use conduction to cool it, so it doesn't need to emit. And two, they never measured the emission. They measured the absorbance, and it was a geometrical problem. So when it's geometry that you get absorption, that is not the same as just having a flat lattice that now the light hits it and is absorbed.
Okay, so I have
geometry.
I have made it my mission to get you into a room with the director of the Pixie Satellite Project. So
there is no director.
There's somebody's got to be in charge.
Fixin is one of the people. I mean, there's a lot of big cosmologists on that project, and yet these same cosmologists did the error on the Planck blackbody calibrator. And there's no question about it, because in the Planck blackbody calibrator, you see when they test it with reflectivity again, they send a wave into it. And what happens is when the wave hits the calibrator, it sets up standing waves inside the calibrator. Well, blackbodies can never have standing waves by definition. They're black. So the calibrators on the Planck satellite aren't properly designed. I've said that a long time ago.
All right, we'll get you in a room with these people. I promise you that. I will apply all of my most charming. I will start the charm offensive tomorrow.
All right, so the poor design, the downstream consequences of misapprehending the material versus geometric contributions towards absorptivity and emissivity. These are some specific cases that flow downstream of not having a material model for this particular light spectrum, the black body spectrum, and not understanding what causes it and how specific it is to that laboratory setting and to that hexagonal lattice, right? And so the whole we've kind of jumped ahead and we're talking about cosmology, but it seems unwise to talk about cosmology without first talking about astrophysics a little bit. That's it for part one. Hopefully you have a good sense of how our understanding of black bodies is going to revolutionize physics. But if you aren't a believer yet, stick around for part two, where we look at all of the specific examples where things are going to change radically in the coming centuries. See you there.